Introduction. What is SMP cache and how does it work? SMP cache is a trace-driven simulator for symmetric multiprocessor cache memory system analysis and teaching. The simulation is based on a model built using the architectural fundamentals of this system. What is cache exactly? Cache refers to the temporary memory known as CPU cache memory, the computer's chip-based function to access more information more quickly than if while using the primary hard disk. The data from the programmers and files you use the most is stored in this temporary memory, which is also the fastest memory in your computer. What is the miss rate in cache memory? Cache hit rate and miss rate are two words that are used to describe a program's cache efficiency. Over a particular time interval, the hit rate is defined as the number of cache hits divided by the total number of memory requests in percentage. The miss rate is calculated by dividing the total number of cache missed by the total number of memory requests and expressing the result as a percentage over time.
How to use SMP cache. Step 1. To configure the SMP cache, click on the configure button on the menu bar on the top left corner and click on the top 3 buttons which are multiprocessor, main memory and cache. Step 2. This pop-up will appear. Next, configure it using the architectural characteristic given like the following. After the configuration is done, save the configuration by clicking the Save Configuration. Next, click on the memory trace to obtain the 3 traces which are CESP, COMP and EAR. After that, to obtain the memory trace, go to Trace, then click PRG, click Choose the memory trace to use. Then, for the experiment, we will either use CESP, COMP or EAR. Under the View Evolution menu, choose any of the 3 which are multiprocessor, cache and memory block. The pop-up will appear. Click on either text or graphic. After choosing the type of evolution, and if the format chosen is text, a pop-up will appear. Press Execute. Then change to Complete and finally Continue. Make sure to click on the Complete before Continue to execute. Next, go to Change Configure and change the block in Change following the question given. After finish setup, Step 10, repeat the Step 7 until Step 9 but change another block change by following the question. And the last step, after finish with all the block in change, repeat Step 5 until Step 9 for a different trace. So we can get the result. Finish.
Based on the table results, which shows the miss rate for multiprocessor, cache and memory block evolution for CEXP, COMP and EAR, each evolution shows a change where the miss rates for each memory traces decreases when the cache size is increased. But for memory block evolution, the simulation did not give any reading and is fixed on 0 as shown in the table. Data results for miss rate of multiprocessor evolution by 3 different memory traces, CEXP, COMP and EAR. By observing this table in this slide, for CEXP, as the block in cache increases until 32 and above, the miss rate showed a consistent result, where it is fixed to only 0.74%. However, for COMP, the miss rate is fixed to 17.908% when the cache size reached 128 and 256, where after that it dropped to 17.274% when the cage size is 512. And for EAR, as the cage size reached 256 and 512, the miss rate is consistent to 6.707%. The trend on the miss rate of cage evolution shows the same pattern as multiprocessor evolution that has been explained. And from both of the table and line graph, we could say that the miss rate for the memory trace CEXP, COMP, and EAR decreases as long as the cage size is increasing.
Question 1. Does the miss rate increase or decrease as the cache size increases? Why? Does this increment or decrement happen for all the benchmarks, or does it depend on the different locality grades? What does it happen with the capacity and conflict collision misses when you enlarge the cache? The miss rate decreases. This is because more data can be stored in the cache at the same time. The miss rate decreases as the cache size increases. All benchmarks showed reduction in miss rate when the cache size increase. The miss rate is affected by the locality grade since larger cache sizes benefit from special locality. When we enlarge the cache, the capacity of the cache can contain all blocks assessed by the program. For this experiment, there are no conflict misses because the cache size is increasing respectively. Question 2. In these experiments, it may be observed that for great cache sizes, the miss rate is stabilized. Why? We can also see great differences of miss rate for a concrete increment of the cache size. What do these great differences indicate? Do these great differences of miss rate appear at the same point for all the programs? Why? The larger cache size affects less chance there will be a conflict, which leads to the compulsory and coherence of misses being reduced. At large cache size, the degree of misses stabilizes because the compulsory miss is independent of the cache size. Great differences indicated the near memory addresses intend to less increase cache size. Thus, it brings about a great increase of miss rate performance. These great differences of miss rate do not appear at the same point of all the programs because miss rates are different for each situation. Question 3. Does the increase of cache size improve the system performance? More cache mean more data can be stored closer to the CPU. The cache memory is advantageous because it stores frequently used instructions or data that the CPU may demand next, and it is faster to access memory than RAM because it is located on the same chip as the processor. In a conclusion, cache size improves the system performance.
In conclusion, the main focus of this group project assignment is to analyze the influence of cache size with miss rates using 3 different memory traces, namely CEXP, COMP, and EAR. After conducting the assignment using SFP cage where configuration to the simulation was made, it showed that cache size does influence the miss rate. This is proven by the data results, whereas when the cache size increases, the miss rate then decreases. But at a certain cache size, the miss rate stops decreasing and is fixed on a specific percentage. Increasing block size, on the other hand, may minimize compulsory misses due to spatial locality, but may actually increase conflict misses because more addresses would map to the same set and could conflict. In summary, cache size have an effect on miss rate. Increased associativity, especially for small caches, decreases the number of conflict misses. And having a low percentage of miss rate can also result in improvement of system performance.